Here we're going to solve our second example using Newton-Raphson's method. We're going to do it by hand using a calculator and a table. Example 6.2. Use Newton's method to solve the equation x equal to x squared e to the x minus 1 for a positive x within an error of 10 to the minus 4. I don't see any zero here. How do we get a zero here? We move that x onto that side. So if we have an equation that has stuff on both sides, we just move one of the sides to the other to get our zero. And now since we're solving the equation, remember that means that we're going to be looking for the function value to be less than this error. So what are we saying? Solution. Our goal is to solve x squared e to the x minus 1 minus x, move that over there, equal to 0 for a positive xn such that the function value of xn is less than our error. And now we're going to write down our function. It's this x squared e to the x minus 1 minus x. So this is the function that we're using for Newton's method. What do we need to know? We need to know if that function is differentiable. And the answer is yes. All of these functions are differentiable and defined everywhere, so there's no problem. What point should we take as our starter point? So we're kind of looking for a point close to some root. Like I said, we will solve this by hand with a standard calculator. Well, not quite standard. We're going to find one that has 3 memory spaces so we can store the iteration point, its function value, and its derivative value. So our function is f of x equal to x squared e to the x minus 1 minus x. And our error is 10 to the minus 4, so 0.0001. And we need a start point, which we'll work out over here, and we also need the derivative. So let's find the derivative. F prime of x equals, this is a product, so 2x times e to the x plus x squared times e to the x minus 0 minus 1. We need a start point that was positive, so we'll take x equal to 0 because we can probably figure that out from here. So f of 0 is 0 minus 1 minus 0. That's minus 1. The important part is that it's less than 0. And then let's go up 1. We'll just keep going up 1 until we get a change in sign. So f of 1 equals 1 times e minus 1 minus 1. E is 2.7 minus 2, so this is 2.7. We're only caring about the sign. Minus 2 equals 0.7, and that is positive. So we've bracketed our root. We don't care about the interval. We're going to start with x equal to 1. I usually take the right-hand side. And if that doesn't work, we'll go back and we'll try x equal to 0. X equal to 1 will work. So we write down here equal to 1. Now, we're going to be using this fancy graphing calculator, but we're only using it because it can store 3 values at the same time. And of course we need the formula that says xn is equal to xn minus 1, this one, minus f of xn minus 1 divided by the derivative of that. And so we need to be able to store 3 values, so that's why we're using the graphing calculator. If you know how to use all the properties in the graphing calculator, it goes even easier. But we're just going to be storing 3 values. So the first one is that b equals 1. So we'll come down here and type 1. We'll come over here and turn it on. Type 1 and store that in A. So now 1 is stored in A. Now we want f of 1. So a squared e to the a minus 1 minus a. So alpha a squared times second ln alpha a minus 1 minus alpha a. And remember we saw it was about 0.7, so we're hoping for that. And we do. First, let's store it to B, and then come down here and write it down. 0.71828. 0.71828. We're only writing down 5 because that's how much space we have, but of course all the decimals are in our calculator. Now we want the derivative at alpha A. So here's our derivative. 2 times alpha A times inverse ln alpha A plus alpha A squared times second ln alpha A minus 1. Enter. And let's put that in C, so store to C, enter, and now we'll write it down. So 7.15485. 7.15485. And now we want to calculate. Remember, this is in A, this is in B, and this is in C. So A minus B divided by C. Alpha A minus alpha B divided by alpha C. So our first iteration gives us 0.89961. We're going to put that back in A now. Store into A. 0.89961. Aha, why do we have an empty column here, you will now ask. And the answer is so that I can figure out the error, I'm going to actually do the function value here, and then when we go down, we will rewrite these two down here. We could just write it down there. We don't need this one, but it's easier for calculating this particular error. So we're going to write in f of xn here. So we saw that 4. We've got a squared e to the a minus 1 minus a. A alpha a squared times second ln alpha a minus 1 minus alpha a. Enter. And now we're going to store that into the B and then write it down. 0.09016. 0.09016. Well, we've got a second decimal. We've got to get to the fourth one. So this is false. And now we rewrite this down here. 0.89961. This is 0.09016. And now we're on to working with the derivative with what we have in our alpha A. So 2 times alpha A times second ln alpha A plus alpha A squared times second ln alpha A minus 1 equals. And we store that in C. And 5.41340. 5.41340. And now we need xn. Xn is alpha A minus alpha B divided by alpha C. 0.88295. We put that into A now. That's our new A. And write it down here. 0.88295. Now we want the function value for that. So a squared alpha A squared times second ln alpha A minus 1 minus alpha A. 0.00216. That goes into B. 0.00216. We definitely have gone down, but we're still not 4 decimal places in. So it's still false. So now we rewrite these. And we're on to the derivative. So what do we have? 2 times alpha A times second ln of alpha A plus alpha A squared times second ln alpha A minus 1. Enter. So 5.15514, and that goes into C. Okay, we're ready to do the new xn. So that's always alpha A minus alpha B divided by alpha C. And we put that into A and write it down. 0.88253. The function value of that, so alpha A squared times second ln alpha A minus 1 minus alpha A. And we're already there. We're down to e to the minus 6. We have 1.3 e to the minus 6. All we needed was something that said e to the minus 5 so that we knew it was less than e to the minus 4. So 1 point something here, e to the minus 6. So we are true, and our answer is this. For safety's sake, we should make sure that these are enough decimals. So we get our calculator out and we'll put in 0.88253. We'll store that to D, and we'll try the function on that. So alpha D squared times second ln alpha D minus 1 minus alpha D. And we're still good because it's e to the minus 5. Notice that it did change sign, so actually the root is between 88253 and 8825345. Let's just see our solution in GeoGebra. So here was the right-hand function, the left-hand function. F of x is the right-hand function minus the left-hand function. Then we calculated its derivative. It calculates it using a command. You do not have to do it by hand here. We put in our error. As always, we kind of looked for the root using GeoGebra. Here is our function. Here is our root. You can see that 1 is very close to the root, so it's probably why it converged very rapidly. Here is Newton-Raphson's method down here. Looks exactly the same as ours. On the third iteration, we get a true here for the value 0.88253, etc. And there's our third iteration. So that is the end of our second example using Newton-Raphson's method.